Hello again. Welcome to part 2 of transformations of functions. So I've already done a video on the transformations that we can apply to a quadratic. And so that video went over the values of a, b, c, and d that you see in this equation right here. So this is like the template for a quadratic. And the values of a, b, c, and d are going to tell us the kinds of transformations that are happening. So if you're a little unsure on what these values represent, go back to my other video on transformations for specifically quadratics. That'll go over the basics. This video is going to move into how we can apply those transformations onto different kinds of parent functions. So today I'm going to be covering square root functions, rational functions, as well as exponential functions. So the first one on the list today is the root function. So we could write that out like this. So we're basically taking the square root of our input, which would be x. And so this is the generic graph for the parent function of square root x. And that's going to be placed right there. So the main point that we want to reference for square root functions is this origin point right here at 0, 0. Usually for a quadratic, we're going to reference the vertex, but for a square root function, when we apply a value of 0 for x, the square root of 0 is 0, so we're going to get this point at the origin. So that's what the generic parent function looks like. And if I wanted to start applying some values to this equation, let's see how that would change things. Okay, so what I've done is I've added a c value and a d value to this function. And we know that a change in the c value is going to cause a horizontal shift, and a change in the d value is going to cause a vertical shift. So these c and d values will change the graph this way. We start here, and I have a positive c value, so that means it's going to be a shift to the left of 2 units. Then our d value is a positive 3, that's going to be a shift upwards of 3 units. So we can see here that our first point, or we could call it the origin of our original parent function, has been shifted based on the c and d values. And so that's a core idea that we can use for square root functions. So the c and d values shift the origin of the parent function. And that works mathematically because if we think about it, we can't take the square root of a negative number, which is why if I look at the parent function, we don't have any negative x or y values. But if I make the c value positive, what that means is I can actually plug in x values all the way to -2, and the function will still work because I will not be taking a square root of a negative. So I really like square root functions to represent why, when we have a positive c value, we're actually making the x values more negative. And let's do one more example here. What about the stretches, compressions, and reflections? So let's say I put a -2 for my a value. What is that going to look like? Well, we know the a value represents a stretch or compression. And in this case, we have a stretch by a factor of 2. So that's going to look like this. But then we have a reflection. It will be a vertical reflection. And so that's going to look something like this. So in this case, for the -2 square root of x, I haven't caused any shift. That's why our origin is still at 0, 0. But I have this stretch by a factor of 2, and I flipped it vertically. And let's do one more example showing off a change in the b value. So as you can see here, the difference in notation between the a and the b value for the square root function is whether or not the value lies underneath the square root or outside the square root. Because for a quadratic, we kind of base it off of whether or not we're in these brackets to have like horizontal changes here and then vertical changes out here. But for square root functions, it's slightly different. Inside the square root function, or inside the square root, would be a horizontal change. So let's try this one. We've got a -2 as our b value. So I know for a fact that's going to be a horizontal reflection. So now we're going this way. And a b value of 2 actually means a compression of 1/2. So this is what we've got so far. But then we also have a horizontal shift of 1 unit to the right. So those would be the changes that I would apply to for this equation. Okay, that about covers it for square roots. Let's move on to reciprocal functions. And I'm assuming at this point, you have enough experience with dealing with all of the possible a, b, c, and d values where you kind of know what's going to happen. So I want to focus on the unique aspects of the reciprocal function with respect to transformations. So if I move the parent function onto the graph, this is what it's going to look like. And you'll notice that our lines are kind of split in two, and we're never hitting the x or the y-axis. And that's because we have a vertical and a horizontal asymptote, and that's represented by these dotted lines. And the mathematical reason for that is if we look at the function, we have 1/x, and if I were to set x to 0, I get a 1/0, but we know that you cannot divide by 0, as the answer is undefined. So that explains why x can never hit the value of 0 on the graph. And in turn, if x can never equal 0, y can never equal 0, because if we can only change the value on the denominator, we can never set this fraction to 0. But all right, how are we going to show transformations with a, b, c, and d with such a unique looking function? We start with the parent function, and the rules are very much the same. If we have a horizontal shift, that's going to be applied directly to the x value. So you'd probably see something like this. So horizontal shift is being applied on the denominator, and the same logic applies. We are going to move 2 units to the left because we have a positive c value. And what you'll notice is my vertical asymptote is following the horizontal shift. So I can tell where my vertical asymptote is going to be on my reciprocal function based on my c value. The way I can tell where my horizontal asymptote is going to be based on my d value. So now we've got a shift of 2 units to the left, but then also 4 units up. So we can see that the horizontal asymptote, its value is based on our d value, and our vertical asymptote is based on our c value. And the notation looks fairly similar to a quadratic, right? Because I have my c value in brackets next to my x, and the d value is kind of outside of everything. Now, a common thing that students get confused about is the a value being applied to a reciprocal function. You'll see a function like this, and you might be thinking, okay, the one which was our numerator, has turned into a 2, but what kind of value is that? Is that an a or a b value? Well, if you think about it, we could rewrite this as 2 times 1 to the x plus 1. So technically, this is our a value. So when we see a change in the numerator, that's actually our a value. So here, if I saw a 2 as my numerator, I know that's going to be a vertical stretch, and that's going to look something like that. But we also have a shift of 1 unit to the left, so it would end up like that. Now it is possible to have a b value on your rational or reciprocal function. It could kind of look something like this. So we have a 2 applied on the denominator, but the reason why it's not very common to show a b value with rational functions is because it's probably easier just to use an a value. Because if you think about it, I could pull out the 2 from the bottom here and simply represent this as an a value of 1 over 2. So it's uncommon, but it is possible to see a b value for reciprocal functions. And of course, horizontal and vertical reflections could also be shown for a rational function, and it would look something like this. So if I wanted to do it vertically, we're going to flip it that way. And if I wanted to do it horizontally, we're going to look like this. Pretty straightforward. All right, last example, we are moving on to exponential functions. The only real change in notation for exponential functions is that we're actually going to apply our brackets onto the exponent itself, because that's where our x value is. So for example, if I wanted to show a c value or a horizontal shift, I could do it like so. So the c value is still in the brackets as per usual, but it's just shown as an exponent applied to the x. And you know what? We might as well plug in a d value as well. So let's look at the shifts that are happening here. Our parent function is going to be right about here. And I can tell that by the fact that if I plugged in a value of 0 for x, any number to the exponent of 0 will give me a value of 1. So I should have that point there as my y-intercept. And also, I'm never going to hit a value for y of 0. So we actually have a horizontal asymptote here as well. Okay, so we've moved 3 units to the right. And I'm actually going to base the change on my y-intercept, because when x equals 0, y equals 1. So in this case, when x equals 3, y should equal 1. And that's kind of what I'm basing the shift on. Because 3 minus 3 would be 0, and 2 to the 0 should give me a 1. Then I have a vertical shift down by 2 units. And what I'm going to use to reference that shift is actually my horizontal asymptote. So in this case, we don't have a vertical asymptote, just a horizontal asymptote, and that will be defined by our d value. So our d value is -2. That means y is never actually going to hit -2, because the value I get on the exponential part of the function is always going to be at least slightly greater than 0. And if I subtract by 2, I'm not quite ever going to hit this line. Okay, last thing, let's look at a and b values. So an a value, we'd probably just represent it outside, 3 times 2 to the x. And then if I wanted to show a b value, I could plug that in right before x, still in the exponent. So we could do like negative 1 over 2 x. So let's look at the vertical stretch first. This one is by a factor of 3. I'm not sure if I'm going to be able to show that here, but it's going to be a huge stretch. So that's going to look something like that. And if I look at our second example here with the negative 1 over 2x in our b value, that is going to be a horizontal reflection. And then we're also going to stretch horizontally by a factor of 2, because we know that when our b value is less than 1, it actually refers to a stretch. So that's going to look something like that. So we flipped it horizontally and also stretched it horizontally. And before we wrap up, I want to quickly remind you, it's always good to factor in a function if possible. And I went over this in my first video, but some students will get confused when they see a function like this, because they might be thinking, okay, I have a b value of 3 and a c value of 6, but if you think about it, we can actually factor out a 3, and we're left with this. So this would actually be the correct way to write out this function if we wanted to find accurate b and c values. So our b value is the same, it's a value of 3, but we can see that we only have a horizontal shift of 2 units to the left instead of 6. So I just wanted to quickly remind you about that key point. All right, and if you would like more practice, feel free to go to www.desmos.com and try graphing some functions of your own. So you can plug in any of these parent functions and just kind of mess around with the a, b, c, and d values and see what happens. Thank you for watching and have a great day.